So we are given the prompt to graph the following function. The following function is r equals 2 plus 4 cosine of theta. So to graph this, we need to do a couple steps first before we can get to the actual graphing of this function. So the first step is to understand the parts of this function. This function is called a polar equation. So here's just a sample to explain all the different parts. So this negative up here would just indicate a reflection over an axis. So say like this is the axis. So cosine would be a reflection over the y-axis. So if it was over here, it'd go over here and vice versa. While the sine here would indicate a reflection over the x-axis. So if it was up here, it'd come down here and vice versa. The a here is part of the a and b are both part of an equation, a divided by b, and that comes into play a little later. I'll explain what that is. The b also indicates the diameter of the equation which would be a circle or a petal. C of theta, the C is very interesting. If it's odd, it indicates the number of petals, and if it's even, then it's 2 times the number of petals. And by the number of petals, I mean the total number of petals in the equation. And I'll explain what petals are just after this. And D would just indicate a rotation about the origin. So let's say we have, there's our little graph, and let's say we have a circle up here. Well, D would indicate maybe it rotates down here, or maybe it rotates over here, you know. And then petals. So what are these petal things that I'm talking about? So petals are very interesting, and I can't really quite describe them because they just look like little loops. But here are just a couple examples maybe to help you understand what they are. So R equals sine of 3 times theta. That 3, because it's odd, indicates the total number of petals on the graph. So 1, 2, 3 petals. They're like little loops. Then in this equation, which would be R equals sine of 2 times theta, because it's even, it would be 2 times 2 equals 4, and 4 would be the total number of petals. So see, 1, 2, 3, 4. That's the total number of petals. And here's another tiny little example. Let's say it's 4 of theta. Then 4 times 2 equals 8, so there would be 8 petals. 1, 2, 3, 4, 5, 6, 7, 8. So now that we understand the parts of the equation, now we need to understand the types of polar equations. So there are 3 main types of polar equations that we are going to talk about real fast. So the first one is the limacon, and that one is A plus or minus, A plus or minus B times sine of theta, or A plus or minus B times cosine of theta. So here's just a couple different examples of the graph. So 1 plus sine of theta, and the 1 for the b is just implied. 1 plus sine of theta would look like this. It would be a little dent instead of like a circle, which is what this little circle or dent is called. And so this is an example where b equals 2, and it's 1 plus 2 cosine of theta, and then that's where we see the little circle. And I'll explain why this is any different right now. So a limacon. Remember how I mentioned way back here that there's an equation called A divided by B. So that little equation indicates the severity of the loop or dent that we see right here. So if A divided by B is less than 1, we are going to see that little loop. If A divided by B equals 1, then we're just going to see a little dent like we saw right here. And if A divided by B is greater than 1, then it's going to look like a really fat D. It's just going to be like that. Okay, so the reason why these two graphs are different, instead of, let's say, this one just being a dent, and that's wrong, and I'll explain why. Because in this one, the A equals 1 and the B equals 1. So 1 divided by 1 equals 1, and 1 equals 1. Kind of self-explanatory. So we have that little dent. In this one, A equals 1, B equals 2, which would be 1 divided by 2, and 1/2 is definitely less than 1, so we're going to see that little loop right there. Okay. So the second type of polar equation is called lemniscates. So this one's a little different. It is r squared equals a squared times sine 2 of theta, or cosine 2 of theta. This a cannot equal 0. I cannot emphasize that enough, because if this a equals 0, 0 times 0 squared equals 0, and 0 times anything equals 0. So essentially this equation would be useless, because r would just always equal 0, which does not help us in any way, shape, or form. So an example of a sine lemniscate would be it along a diagonal of the, so this would be a diagonal, and then this would also be a diagonal. So the loop would be here, or the loop would be here, or it would be on both. In this one, it's going to be along the actual axis itself. So it'll be over here, or it'll be over here. But in either case, it will be, instead of a diagonal, it'll be horizontal or vertical. And this is kind of a theme that you're going to see in the rose curve as well, which is the third type of graph. So this one is r equals a sine of n of theta, or cosine n of theta. Again, a cannot equal 0, because then the entire equation equals 0, and that does not help us at all. And also in this case, n has to be greater than 1, because then also it doesn't affect the graph in any way. If n is 1 or 0, again, it renders the graph not really helpful. And it wouldn't quite be a rose curve. It would just be an equation. So in this case, let's say we have 1 times sine 2 of theta. That would, again, show our little petals here, and it would be 4 of those for reasons I explained a little bit earlier about the petals. Same with this one. If 1 times cosine 2 of theta was graphed, it would go along the axis just like this was along the diagonal. Okay, so now our third step. We want to figure out what kind of polar equation is our function and understand the parts of said function. So here, remember our equation is r equals 2 plus 4 cosine of theta. Now we can compare that to our types of polar equations. So does it follow this pattern? No, because it's a cosine. Does it follow this pattern? Yes, because it's a cosine. Okay, now let's compare. The a would be the 2, the b would be the 4, and it doesn't have anything else that deviates from this, so it has to be a limacon. Here we go. So now that we know that it's a limacon, we will understand that our graph will be unique. It will have a little loop in it, or it will have a dent, or we'll have a dent, or it will be a fat D. So now we're going to figure out what it is, okay? So let's go ahead and plug in our little equation that we talked about earlier. So that would be 2 divided by 4, which is a half, and a half is definitely less than 1, so we are going to see our little loop here. And also going back to look at the other part, see if there's anything else we can figure out. 4 is the b, and b is the diameter. So our little circle is going to have a diameter of 4. So now that we know what our graph is going to look like, we are going to plug in angles for theta to start actually being able to graph our function. Because without these points, it's just kind of like, I'm doodling. So here, let's see what happens when theta equals 0. What does r equal? So let's get as simple as we possibly can. So what is cosine of 0? That is 1. And so remember, our little equation was cosine of theta times 4 and then plus 2. So we're going to go ahead and put cosine of theta times 1, which is just 4. So then it would be 2 plus 4 equals 6. So r is going to equal 6 when theta equals 0. So then we kind of do the same thing with each other point that we want to do. So theta equals 45 degrees. Cosine of 45 is square root of 2 over 2. Plug that in. We get 4.83. So r is going to be 4.83 when theta equals 45 degrees. And then really, I'm not going to bore you with the rest of these because you get the point. And when theta equals 90 degrees, r equals 2. When theta equals 135 degrees, r equals 0.83. When theta equals 180 degrees, r equals -2. So now we need to plug these in. So our points, let me fix that. Maybe, no, you can't see that. Let me fix this. R theta. So this is what our points are going to look like. So r is going to go here in the front, and theta is going to be here in the back, so x and y. So let's go back to our first example. R equals 6, so then it would be 6, and then theta equals 0, so it'd be 6, 0, which is this one. So these are all our points just plugged in real fast. And so notice I didn't go past 180. I didn't go all the way up to 360, which would be a perfect circle. And the reason I did not do that is because I can use symmetry to complete the graph. Now you can graph all the way to 360 if you want to, but then this just saves you a lot of time in the long run. So yeah, I can use symmetry to complete the other side. So now that we have all our points here, we can literally just graph the equation now. So we see we put all our points here, and this is what our graph is going to look like. Ta-da! We did it! Yay! Hopefully you understood what I was trying to explain to you. Yeah.